All right, in this section, we're going to discuss something known as integrated rate laws. First, discussing concentration versus time. It is useful to be able to predict the concentration of a reactant at a specified time after the reaction has begun. The equation that describes the relationship between concentration of a reactant and time is known as an integrated rate law. Since the equation that describes rate as a function of concentration is different depending on the order of the reaction, the integrated rate law is different for 0, first, and second order reactions. Only the plot of concentration versus time for 0 order is linear. The next few slides will demonstrate how to make first and second order plots linear. The reason that that's important is that once a reaction is linear, or once a graph or a plot is linear, you can use that to do some data analysis. Let's begin with a 0 order reaction. Recall that for a reaction where reactant A produces products, the rate law for a 0 order reaction is rate equals K. Since the concentration of reactant A at some time t is decreasing at a constant rate, right? A constant rate equal to K. The concentration at any time t can be given by this equation. The concentration of A at time t is equal to minus Kt plus the concentration of A at time 0. This is the integrated rate law for a 0 order reaction in which the concentration of A0 is the original concentration of A, and that concentration is decreasing over time. This relationship is linear. A plot of concentration versus time would give a straight line with a slope equal to negative K. Here's a graph for the integrated rate law for a 0 order reaction. So we're graphing this line. Concentration of A at time t equals minus Kt plus the concentration of A at time 0. This is what the line would look like. The relationship is linear with a slope, the definition of slope, rise over run. The slope here, minus K, and the y-intercept up here is the initial concentration or concentration at time 0. Graphing experimental data is useful in determining the order and the rate constant. If a plot of concentration versus time gives a straight line, then we know it is a 0 order reaction. First order. Recall that for a reaction where reactant A produces products, the rate law for that 0 order reaction is rate equals K, the rate constant, times the concentration of A. Since the concentration of reactant A at time t is decreasing at a continually changing rate, we need some calculus to reveal that the concentration at any given time t is given by the following. So the natural log of the concentration of A at time t is equal to minus Kt plus the natural log of the concentration of A at time 0. How we get this is not the most important part of the unit. So the calculus required for this, I don't want you to worry about. I just want you to know this equation and know that this is the equation for a first order reaction. Okay? This is the integrated rate law for a first order reaction in which the concentration of A0 is the original concentration of A. This relationship is not linear. To graph this relationship as a straight line, right? It's not linear because we have these natural logs, which are exponential, okay? But I want to be able to evaluate it. And it's easy to evaluate straight lines because we can see things like the slope. So in order to get a straight line, we need to plot the natural log of the concentration versus time. So if I plot this entire thing as my y-axis and t as my x-axis, I will get a straight line. and the line will have a slope equal to minus k, right? Remember that y equals mx plus b. So if I plot this entire thing, natural log of concentration, rather than just concentration, I'll get a straight line, and that line will have a slope equal to minus k. Here's a graph for the integrated rate law for a first order reaction. So you can see on the y-axis, I've graphed the natural log of the concentration of A. On the x-axis, I've plotted time. I get a line. The slope of that line is equal to minus k. The relationship was made linear by plotting the natural log of the concentration of A on the y-axis. The line has a slope of minus k and a y-intercept of natural log of the initial concentration of A. Graphing experimental data, again, is useful in determining the order and the rate constant. If you graph natural log of A versus time and get a straight line, then this is a first order reaction. If I plot just concentration versus time for this reaction, you can see I don't get a straight line, right? This is not linear. And that's how I know it's not zero order, okay? Because concentration versus time for a zero order reaction is a straight line. If I don't get a straight line, then I know it's not zero order. When the same data is plotted using the natural log of concentration instead of concentration, so natural log of concentration versus time, we get a straight line. This reaction then is first order. The rate constant K can also be determined from this graph. We could find the slope of this line, and the slope of that line is equal to minus K. All right, now let's look at the integrated rate laws for a second order reaction. So remember that for a reaction where a reactant A produces products, the rate law for the second order reaction is rate is equal to K times the concentration of A squared. Remember that the concentration of A with respect to time is decreasing at a quadratic rate. We can do some calculus to reveal that the concentration with respect to time is given by the following equation. 1 over the concentration of A with respect to time is equal to K times T plus 1 over the concentration of A at time 0, or the initial concentration. This is the integrated rate law for a second order reaction in which this concentration of A0 is the original concentration of A. This relationship is linear. If we plot concentration of A to the minus 1, or 1 over concentration of A on the y-axis versus time on the x-axis, we would get a straight line with a slope of K and a y-intercept equal to concentration of A 0 to the minus 1, or 1 over concentration of A, right? So this is our y-intercept. This is our slope K and T plotted on the x-axis. Here's a graph for the integrated rate law for the second order reaction, 1 over concentration of A at time T versus time. So this relationship was made linear by plotting the inverse of concentration, or 1 over the concentration on the y-axis versus time on the x-axis. This line has a slope of K and a y-intercept of 1 over the initial concentration of A. Graphing this data is very useful in determining the order of the reaction and the rate constant. We know the rate constant is the slope, and we know that if this graph, 1 over concentration versus time, gives a straight line, then it is a second order reaction. All right, so here's an example of what this data looks like for a second order process and how we can use graphical analysis to determine the order of the reaction and the rate constant. So the decomposition of NO2 at 300 degrees C is described by this equation. 2NO2 gas produces 2NO plus O2. Okay? Determine the order of this reaction by plotting the data and determine the rate constant. So here's what we have. We have time data every 50 seconds and then 100 seconds. And then the concentration of NO2 decreasing with respect to time. So in the following slides, we're going to graph this and see what's going on in order to determine the order and determine the rate constant. Okay, so the first thing I did was plot the natural log of the concentration data versus time. This is a curve. This is not a straight line. That means that this reaction is not first order. Okay? The next thing I did was plot 1 over the concentration of NO2 versus time. This gives a straight line. And what that means is that this reaction is second order. Okay? If I plot 1 over concentration versus time and get a straight line, then that indicates a second order process. Once I know that it's a second order process, I can find the slope of the line. Now, the rate constant is the slope of the line. That's the second thing we need to find, is the rate constant. And so it's fairly straightforward. You just have to pick a couple of data points, and I'm just going to pick a couple of easy ones where the slope is change in y over change in x. So if I pick this data point, this is 150 minus 100. If I just pick here and here. And then the time is 100 minus 0. Okay, so 150 minus 100 is 50. Divided by 100 is about 0.5. If I use my mathematical graphing tools and find a better line of best fit, the slope is more exactly 0.54. Molarity to the minus 1, seconds to the minus 1. Okay, so here's a summary of rate laws and integrated rate laws for a reaction where reactant A, generic reactant A, produces products. For a zero order reaction, the rate is equal to the rate constant K. In slope-intercept form, y equals mx plus b form, we plot concentration of A with respect to time on the y-axis, time on the x-axis. Our y-intercept is the initial concentration, and the slope is the negative rate constant K. On your AP reference sheet, you are given this equation. You're just given it in a slightly different form, where you have the change in concentration, the difference in concentration, equal to minus KT. Okay? For a first order process, rate is equal to K times the concentration of A. And for our integrated rate laws, in order to get that straight line on our graph, we plot the natural log of concentration with respect to time. On your AP reference sheet, again, this is written as a difference in the natural log of concentration at time t minus natural log of concentration at time 0. Okay, just in a slightly different form. And then finally, for a second order process, the rate is equal to K times concentration of A squared. And here's what our integrated rate law looks like. It's 1 over, we're plotting 1 over the concentration of A at T versus time on the x-axis in order to get a straight line. And again, it's in a slightly different form on your AP reference sheet, where the initial concentration is on the left side of the equal sign. You have access to this on your reference sheet, but make sure you familiarize yourself with it as you're preparing to answer questions in this section.